Okay.
And
Record to the cloud?
yes,
Oh, good.
so it's recording now.
Okay.
And it's sharing.
Good.
So we're good.
We're good.
Okay.
Our next talk is Scott Chapman, who will talk about UFDs.
Okay. So thank you, Mel, for the kind invitation. And so the talk is going to be, this is more of an algebra talk. It's got a little bit of discrete stuff in it. So I hope some of you find it interesting. Now, most of what I'm going to do is in this first paper. And the original version of that paper was written for the American Math Monthly. And when I sent it to the monthly, the referees immediately came back and said, this is too technical for the monthly. And I ran the monthly for a long time, so I was kind of stunned. But so I tried it in another journal like the monthly, and the referee said the same thing. So we took the paper and kind of rewrote it more as a research paper. And it's going to be in the bulletin of the Australian Math Society, I think later this year. There's an old paper there I've listed as 2 that I'm going to pull an open problem out at the end that's still open. And all the proofs, or almost all the proofs I'm going to go through today, are in either A, B, or C here. These are papers over the last 15 years, and all of them are in the Journal of Algebra. Okay, so this is actually more of an algebra paper. But what I want to do is start with a definition that I think almost all of us in this room have been recruited to teach abstract algebra at one point or another. And the grad students that are here, if you haven't yet, you will. And so here's something that you usually do in the first course. Here's the good old basic definition of a unique factorization domain. What I would point out about this is 3 things. The first is in the second line, there's a requirement that every element, every non-unit in D can be factored as a product of irreducibles. That's not true in all integral domains, but talking about ones where that doesn't happen is another talk. And obviously 1 and 2 here. So what the definition says is if you're given something that in algebra we call atomic, meaning everything can be factored into irreducibles or atoms, if you're given a factorization of an element 2 different ways into irreducibles, the number of irreducibles up there is equal, and there's this magic permutation that reorders things so that they line up as associates. Okay, so all of us have seen this before, and it's not a surprise. But what I am going to do today is talk about why, in some sense, you don't really need number 1. I'm going to rewrite this definition so that all you have to do is look at factorizations of equal length, which I've had people tell me is kind of ridiculous, and other people tell me is really interesting. So I guess beauty is in the eye of the beholder. So to do this, I'm going to use a new property that I'll define in a second called length factorial. The area that this comes out of, Alfred and David spoke yesterday about factorization material. So over the past 40 years, these problems has grown into its own discipline. And most of what is done in more generality in a commutative cancellative monoid, which is what the multiplicative part of an integral domain really is. So most of the things in the literature are stated in more generality in terms of monoids. And I'll begin in that manner today and kind of pull back eventually. So again, if you look through the recent literature, more of it focuses on monoids in general than rings. But again, one of the points to the talk here is that factoring in an integral domain, while it does live within the world of monoids, that second operation, the addition operation, does force some really strong structure on the multiplicative operation. Okay. Now, the previous definition was for a UFD, Well, I could rewrite that from a commutative cancelative monoid very easily. So I'll use the term UFM instead of UFD when I'm doing this in a little more generality. Okay. So again, the point is going to be that I'm going to simplify that UFD definition, but it's not going to work in a more general monoidal setting. And I'll illustrate that here as we go on. So again, the last comment here is while the recent literature doesn't emphasize, the properties of a ring in the factorization setting, they're important. And I think this result kind of shows that. So here's some notation. I really don't need all of it, but again, in the next few slides, M will be a commutative cancelative monoid. Script A of M will be its set of irreducibles or atoms. If M is generated by its atoms, it's called atomic. Everything can be factored as a product or sum of irreducibles. Let's let M cross be the units. The quotient monoid M mod M cross, which is usually called M reduced, is a monoid with a unique unit. And normally in factorization theory, people pass to the reduction so you don't have units flying around everywhere, which don't really play a role in what's going on. Now, a factorization of irreducibles, let's say alpha 1 down to alpha of n is equal to beta 1 to beta sub m, is called non-degenerate if you can't cancel. Okay, in other words, that's what those three lines kind of add up to. Everything on the left does not appear on the right, either bluntly or via associate and vice versa. Okay, so a non-degenerate factorization is one that can't be reduced any further through simple cancellation. Okay, now if you're in a commutative cancelative monoid, every non-prime irreducible, non-prime, is contained in a non-degenerate irreducible factorization. That's going to be important as I move on here this morning. Okay, now, the first definition we saw yesterday in the talks of Alfred and David, but just let me review this for a second because it's going to play a role in what I do here today. An atomic commutative cancelative monoid is called half factorial if whenever you have two different factorizations, the xi's and the yj's here are irreducible, then the number up there is the same. So essentially, from the previous definition, just number 2, not number 1. Okay. Excuse me, number 1, not number 2. Okay. The links are going to be the same. And I'll come back to that in a second. Now, this is a less known kind of object that over the last 10 to 15 years has become kind of an object of some study. And again, it's a little subtle. So look at this carefully. M is going to be called length factorial if whenever you do have two factorizations of the same length, they're identical. Now, again, you've got this this permutation that lines everything up via associates. Okay, so these are different things. Okay, but the difference is a little bit subtle. If you went back to the definition, essentially, as I said before, the first one throws out number 2, and in some sense, the second one throws out number 1. Okay, but so half factorial and length factorial. So just to mention, and a couple of these examples were mentioned yesterday, there are these things flying around out in the literature. For half factorial, the most prevalent example is a ring of algebraic integers of class number 2. Karlitz showed that this is a half factorial domain. If your algebraic number ring has class number bigger than 2, then it's neither half factorial nor length factorial. You can easily argue those two things. Any 2-generated commutative cancelative monoid is length factorial. And that's a really strong example because it's hard to find length factorial things that are more complicated than that, but there are some. a Poisson monoid. This two generator property works in the set of Poisson monoids, which are additive submonoids of the non-negative rationals, and that includes numerical monoids, non-negative submonoids of the non-negative integers. Okay, linked factorial Krull monoids were recently characterized by Alfred and Zong in 2021. So these things live in the literature, and if you take those two definitions and look at them carefully, you get this very simple theorem. A commutative cancelative monoid is factorial or a unique factorization monoid if and only if it's both linked factorial and half factorial. And I did not use this was a challenge for me if I remembered how to LaTeX a Venn diagram without looking it up. Somebody was talking about Claude yesterday. I went in last night. Yeah, you can get Claude to do this and not have to memorize the commands. But I did remember how to do it. I was really proud of myself. But here's the picture. And so all four of the areas in that diagram are populated. There are half factorial monoids that aren't UFMs or LFMs. There are LFMs that aren't UFM. So there's stuff in all the areas up there. Okay, you can't refine this picture any further. But our goal is going to be that if you change monoid to integral domain, there's a significant refinement that we'll see in a few minutes. Now, there's a little bit more notation that I have to use here. Alfred did a little bit of this yesterday. You can write factorizations in these things out many different ways. I'm going to do it in the free monoid on the atoms using that product symbol down there. So if you had a factorization in M where X is K1 copies of X1 plus K2 copies of X2 ... down to K sub T copies of XT, I'm going to write it in the free monoid as such. Okay. If M bullets the set of non-units of your monoid, if I take a non-unit, Z of X, we saw this yesterday, is going to be the complete set of factorizations in the monoid. Okay. Now, here's an object which has become popular in the literature around this type of thing, again, over the past 10, 15 years. So if I take an element X, I look at this set Z of X. I'm going to build a graph on the set of factorizations, and I'm going to put an edge between two factorizations if they share an atom. So this is why I'm here, right? This is the discrete part of the talk. So I get a graph, and it's called the Betty graph of the element B, okay? We're going to call an element a Betty element if and only if its Betty graph is disconnected, okay? And I'll let Betty of big M denote the set of all Betty elements of M. And what you can find in the literature is if you want to factor things, much like Alfred and David were trying to do yesterday, knowing what these Betty elements are is important. In fact, what they are in some sense is the set of minimal relations amongst the atoms in some sense. Now, I want to give you an idea that, if you have students and you want to give them a little project, this is a great thing to give them. Give them something and say, write out the Betty graphs of these things. I'll start to do that here. And to get the Betty graphs more than just really simply trivial, I'm going to have to take somewhat of a complicated monoid. So let's look at the numerical monoid S generated by those 7 numbers. 11, 12, 13, 16, 17, 18, 21. Those are all necessary generators. So you get this nice numerical monoid for people that work in these things. There's all kinds of things now you can look at that monoid and play with. But one thing is there's a wonderful program in GAP where this is preloaded in, and it'll spit the Betty elements back at you. Throw your numerical monoid in. Here come the Betty elements. And there they are. There's a bunch of them. 24, 28, 29, ... If I use this tuple notation to kind of simply represent factorizations in that monoid. I'm just going to pull two elements out, 45 and 43. Here are their factorizations. There are 4 factorizations of 43. There they are, Z1 through Z4. There are 7 factorizations of 45. There they are. You can check if you want to make sure that's right. And there are their Betty graphs, okay? You'll notice the one on the right, the Betty graph for 45 is connected, okay? And the Betty graph for 43 is not. 43 is a Betty element and 45 is not, okay? And it's not hard if you work in numerical monoids. There's a point in the monoid from everything onward. There's no Betty elements. You know, these graphs get bigger as you go down the line. And so, but anyway, you can build Betty elements and look at their graphs. Why would one want to do that? Well, because in the paper, in the Australian Math Bulletin, there's what I think is a nice characterization of length factorial, which builds on the original characterization, because the original characterization of length factorial was that 1 and 3 were equivalent. And let's look at it that way first, because I think that's a really nice characterization. So M is length factorial and not factorial is equivalent to, now let me boil this down a little more simply than the way it's written out there. There is a factorization that involves all the non-prime irreducibles, where there's a group of them on one side and a group of them on the other. And every non-degenerate irreducible factorization of M is a power of that one single factorization. And generally, we call this thing the master factorization in the monoid. Okay, so if you have a master factorization, the thing's length factorial. If you don't have a master factorization, it's not. So that's a really strong property. It's hard to have a master factorization. Now, what we showed is number 2, is that these Betty graphs I was just looking at, if the thing's length factorial, there's exactly one Betty element, and its graph is a empty 2-vertice graph. There's 2 different factorizations of differing length, because there's examples where there's one Betty element with 2 different factorizations of equal length, and that's half factorial and not length factorial. Okay, so these 3 things are equivalent, and I think I scratched out some proofs, but I just pointed back to other papers. 1 and 3 are equivalent due to that original paper by Kuykendall and Smith, and 1 and 2, there's a proof of that in C, which is a paper I was an author on. Okay, so you've got a nice characterization of length factorial. What good is that? Well, let me take that theorem and apply it to integral domains, or begin to apply it to integral domains. And to do that, I'm going to reach back into the literature for a couple of other things. If you are a veteran of a class where you use Kaplansky's book, this idea is pulled out of Kaplansky's book. An integral domain, which is atomic and has finitely many atoms, is called a Cohen-Kaplansky domain. I think Kaplansky has some exercises in his book about the rings, the community of rings book. And in a broader sense, I'm going to call an atomic integral domain that has finitely many non-associated, non-prime irreducible elements, a generalized Cohen-Kaplansky domain. So 2 different things. But I need the generalized ones for the next few minutes. Okay, so let's look at a corollary to that big theorem. Let M be an atomic monoid, which is length factorial and not factorial, with master factorization 1. Every non-prime irreducible of M appears in 1, and hence M must have finitely many non-prime irreducibles, so it's a generalized Cohen-Kaplansky domain. Now, these things have been studied actually pretty intensely 20 to 25 years ago, so there's a lot of literature about them that you can use, and using some of that, you can prove the following theorem. An integral domain D is factorial if and only if it's length factorial. Okay. So obviously from left to right is trivial, but you can come backwards. Okay. And there are 2 proofs in the literature, maybe 3. And this paper that I just wrote with Kuykendall, there's another proof that hinges on generalized Cohen-Kaplansky domain. So I want to make sure this is not, there's no misunderstanding here. This is not a new result, but there's a different proof of it in this paper. And just to show you that our proof's probably the simplest one, I think. It does rely on material on generalized Cohen-Kaplansky domains, but I can scratch it out there in 5 lines. Left to right is trivial. To go backwards, if you've got something that's length factorial and not factorial, by the corollary, it's a generalized Cohen-Kaplansky domain. By the properties of a Cohen-Kaplansky domain, if it's atomic and it's not factorial, there are atoms, U, V, and W, which are distinct so that U squared is VW. You're done. It can't be length factorial in a very simple manner, right? At the level 2 in some sense. So I get to use my LaTeX skills again. So for integral domains, that Venn diagram looks like that. So the length factorial and the half factorial stuff is the same. There's half factorial stuff in the atomics. And for integral domains, you can populate all 3 of those things. So the picture changes wildly. Now, what does that do to us? Well, the first comment, I'm not out of time quite yet, good, is there's a really nice little corollary from this that I think is interesting, that I wouldn't have believed this was true until I saw it. So take an atomic integral domain that's not a UFD. There's a positive integer n and a non-degenerate factorization where each side is of length n. There's a non-unique factorization of equal length in any non-factorial integral domain. I couldn't believe that when I saw it, but it's true. Okay, it follows from everything up there. And here comes the alternate definition. Let D be an integral domain in which every non-zero can be factored as a product of irreducibles. D is a UFD if whenever you look at equal length factorizations, they have to be the same. Okay, so all you have to do is check the equal length ones. Now, for my last minute or so here, let me talk about how we might not be done. And I mean that by might, because there's an open problem here that survives from that 30-year-old paper I referenced. And it kind of goes like this. I'm going to make a new definition. It's called quasi-n factorial. And what it means for a monoid to be quasi-n factorial is fix n bigger than or equal to 2. That means if whenever you look at equal length factorizations into irreducibles, they're unique. Okay, it doesn't mean that you're in a UFM or a UFD, but the equal length factorizations are the same. And so this 30-year-old paper goes on a journey where the authors, me being one of them, tries to build a quasi-2 factorial integral domain that is not factorial. And we never did it. The paper's just a big list of conditions. If the domain does this, you can't do it. If the domain does this, you can't do it. So we never build one, okay? And so that's essentially an open problem. Is there an atomic integral domain that's quasi-n factorial for some n bigger than or equal to 2 that's not factorial? Now, I think the way you approach that problem in the best sense is let n be 2. Okay. We think the answer is no. We don't have a proof, but our gut is telling us that the answer is no. But think about this. If the answer is no, let me go back. If the answer is no, you could take this alternate UFD definition and change n to 2. And then this really blows my mind. If you've got an integral domain, if you want to check to see if it's a UFD, you only have to check factorizations of length 2. Now, I don't know that that's true. But if if I guess I'm going the wrong way. Yeah. But if there does not exist such a thing, then you can simplify the definition of UFD even further. So I hope you enjoyed that, and thank you. Thank you.
Yeah, I wanted to pan and zoom the camera so people can see better.
Can you get that out of this? Oh, okay. So, yeah.